So it's my pleasure to introduce Professor Anindya Goswami, who is a faculty in mathematics department, ISA Pune. So Anindya completed his graduation from ISC in 2008. He spent 3 years abroad doing postdoc and returned to India in 2011, joined ISA. So his research interests are stochastic process and control problems. Today is going to talk on the data-driven option pricing using single and multi-asset supervised learning. So I invite Anindya.
Thank you very much, so yeah, I did my PhD from ISC, so that is my connection with ISC home. Okay. So this is one work which is just my one effort to explore a new branch, and this was basically inspired by enthusiasm of a couple of students. So I mean, I have written their names, Atharva Takshale and Sharan Rajani. Both of them were undergrad students. So they were very enthusiastic about machine learning application in option price, any field of mathematical finance. So so basically, I mean, I must say that it is their motivation and their inspiration which brought me in this subject area. Okay. So let me start with very conceptual introduction about uncertainty of the financial market, which does not require any prior knowledge, has inherent uncertainty. This much I can assume that all of us agree. And then the oscillation increases, then we say that the volatility factor is more. So that is the I mean, shortest introduction of volatility factor. So volatility factor is measured in various different ways. It is defined as the annual standard deviation of return of the stock, but it has to be computed. It can be computed in many different ways, and various different methods would give slight different values. So this is the thing that this factor captures the fluctuations or uncertainty of the asset price dynamics. So why should volatility be of our discussion? Because there are many instruments traded in the market regularly, which we call derivative, because the price of those instruments are derived from price dynamics of another underlying asset. Okay, so this is one very short example of call option price, call option. Okay, so here is by the buyer, the seller, not of the stock, but of a contract, which you call call option. This contract basically says, I mean, that this boy, if possesses this contract from the girl, that means pays some money, okay, maybe $1 premium, and possesses this contract, then gets a right, the right of buying 1 unit of stock from the girl with a very fixed price, and that price is determined today. So today you can think the 1st October, and next future is December 1. So between these 2 dates, October 1 and December 1, 3 months, there could be lots of fluctuations, but the girl has to sell 1 unit of stock at this price. So that puts risks on her shoulder. So she should not agree unless she is getting paid sufficiently. So the question is that what money is sufficient? So that is main question of option pricing. So this is the way that, I mean, this derivative actually gives the opportunity to transfer risk from an investor to another and pay some money for that. So we understand that such type of derivatives, since those are traded and their intrinsic value depends on the uncertainty of underlying stock price. So understanding the underlying uncertain stock price is very important. Okay. However, that is hidden. I mean, it is not quoted anywhere. One has to figure out, and those things, need not be constant. So those, uncertainty factor might also evolve, and how it evolves, that is also, not very clear. One does not know about future, and it is all about future, correct? Future uncertainty and lack of knowledge of future is the main difficulty. Okay, so for this, actually, there are lots of theoretical approaches. Of course, the famous work of Black, Scholes, and Merton, which laid foundation of theoretical pricing of option by assuming theoretical dynamics of asset, like modeling the asset price by stochastic differential equations that we all know. However, those assumptions on the theoretical, model of the asset price may not be very close to the actual, empirical results. Okay. So here I'm just trying to say here that the success or failure of theoretical option pricing and hedging is closely tied to the success in capturing the dynamics of the underlying asset. Simplified assumptions like Black, Scholes, Merton, those are, those give very nice mathematical tractable formula of options. However, those are, little less useful because the assumption is too simple. On the other hand, complicated theoretical models one can come up with, that is like mathematical extension generalization of the results, but those models then become hard to calibrate. So then also these are not so much useful. So that gives the scope of further improvement, and at this scope, at this space, data-driven approach comes in. So since this is a hard problem, okay, adaptation of data-driven approach in pricing option contracts is gaining attention, okay, because of this, lots of competition power in recent time. So what do we mean by machine learning approach? Okay, I really appreciate. So that way, if I try to say, okay, I think my internet connection is not stable, I should switch the network. Just a minute. Sorry for interruption in between. I should have switched before. Okay, I mean, just feel free to stop me in between if connection becomes worse again. So then I would switch because it is going to take me time. Okay, so here assume that we have a bivariate data in a very simple settings. Okay, so here X is coming from not maybe scalar, but from a equilibrium space E, and Y is output variable that is also coming from a set of categories. So then, an algorithm is trying to learn this association between X and Y. And then, basically that means that exploring a function F, which is unknown or hidden, that which actually explain this association. So there are the ways that since these are noisy things, just X to Y is not a very good idea to look for. One should look for from X to set of all probability measures in C. So instead of Y, trying to find out the distribution of Y. So that type of association. So instead of just point to point, but point to cloud kind of thing. Okay. So that is the way to do. And then, when we try to find best fit such association, one should find out a particular distance concept between the set of such maps. So for, probability measures, this like cross entropy measures, it turns out to be very useful, and that is in this type of model algorithms. Okay, so So then this type of algorithms, there could be various different way to implement the algorithms. Okay, these diverse algorithms with the different approaches are available in many different packages, etc. And people keep on improving this search. So that is all about machine learning. Okay. So now for ML approach in option pricing, I would just like to comment that as if you have seen the example of call option price, there the price of the option basically depends on the price of stock in some way, because if stock price in future is too high, however the girl has to sell that stock at only $10 to the buy, then the worth of the contract is also more, because that is giving high value to the buyer of the contract. So that means price should increase. So that, I mean, non-decreasing nature or increasing nature of the option functions, one can deduce intuitively. However, precise values one cannot come up with, I mean, unless one fixes very, very precise dynamics or has a very precise understanding of the relationship. So that is the thing what machine learning approach is trying to do, or theoretical option price is trying to do, is that finding out these unknown functions. So here is also looking for one unknown underlying function, deterministic function is there. Okay. So how is the data here? Of course, here data is not XY point that way. I mean, one has this type of data. So every day you have data of the corresponding asset price. So here I have taken index. Here 6,301.65 is the price at that day, the 1st January 2014, and then. But there are so many rows, because at that same day, on the same asset, multiple different sellers sold multiple different contracts, okay, having different strike prices. Instead of $10, some another writer possibly wrote something with $11 kind of things, you can imagine. So, and also with various different time to maturity. I mean, not only 1st December maturing, but maturing on 1st January or maturing on 1st November or whatever. So these are the things, so that's why every day you have many such type of data. One has to figure out that which data to consider and how to consider. So you understand that there are so many parameters involved here. Okay, so what we are going to search and going to find out, that answer should also depend on these parameters like strike price, time to maturity, etc. Okay, so for data cleaning, from raw data, we just filter I mean the data which are less credible. So here there is very important concept in math finance that is called no arbitrage pricing. The pricing should not be unfair. Okay. So here, for this reason, one should look for, one should consider only those data which are reliable. That means those contracts have been traded sufficient number of times, or many people are interested. So that's why the price at which that option, that contract was traded, can be regarded as fair price. So removing these 0 kind of things actually is important. Okay, so then part of the data is taken as training data, and last part is taken as stage data. Like it's a time division, like old data as at training and recent data as at testing data. So what is the overall plan? Overall plan is this kind of, the data set is there, and then from the data we should articulate what is the input and output. Output is like option price, input is like information of the asset price. There are 3 different approaches what we proposed, and then from this output and input, these things we feed in to train data set, and this blue line is output data, red lines are flow of input, and then when this model is trained, and then for test data set we just give the input data, and output data we keep for our benchmark testing. And so then our trained model, given this input, produces a prediction, and then whatever model prediction is there, that is then compared with the outputs. And that comparison can also be done in many different ways. Okay, so we propose two different, we actually consider two different, error matrices. So there's the overall plan. So since we don't have much time, I would not go into details of all this, but I would of course talk about the literature. So I mean, this subject is not so new. It is the first paper appears in 1993. Okay. So where the computational resource was also not tremendously, good, and yeah. So a neural network model structure. Okay. And then this 1994 paper also almost like same time, that also appeared by Hutchinson, and then other works rather more recently, which then explored many this direction in more details, and then figured out that modularity or some other ways to segregate the data so that not a single model, but a battery of the models work better. So that is the thing, this is 2016 paper, that also exploits this direction of modularity, that option pricing with modular neural net. And also another concept, homogeneity hint, that basically says that option price is like of order one, homogeneous of order one in stock price and strike price. That reduces the dimensionality and yeah, basically that reduces the dimensionality and computational expense. So these are the things, but we also have explored, and we have also used homogeneity hint, etc. And what we have observed that using that one can build a model which is quite more general, that when trained using one particular data, like NIFTY50 data, and it is successfully predicting option prices for that model, I can again use for finding out option prices for the bank nifty data, okay, and other asset classes on option contract. So that is the kind of investigation what we were interested in. Why? Because one thing is that that type of like transfer learning was absent in the literature, and secondly, thing is that often there are some option contracts on some underlying for which we do not have sufficient data. And if we already train the model using data of some other assets for which we have sufficient good quality data, then we can perhaps use that trained model to solve problems of option pricing for less traded assets. So that is the whole purpose of the investigation, and we were trying to investigate the success or failure limitations of this approach. Okay, so in our approach, now I'm going to give a little more details, maybe. Yeah, maybe I just to go through this very quickly. So basically, instead of prescribing a single option price, we prescribe an interval option price. Okay, an interval of option price. Okay. Because in the market is like is incomplete, so there could be multiple. The length of the is that we have rather fixed that length of the interval, but found out that where does it locate. Okay, so yeah, so that is one thing, and then we therefore output as interval. And also, like as I told earlier, that homogeneity hint is something that we have exploited to make it scale free, so that the transfer learning can happen efficiently. So yeah, so and then then whenever we are talking about option price as an interval, then exactly finding out the width of the interval is also study some asymptotic things so that we get one particular decide one particular length of the interval where the errors etc stabilizes. Okay, and the error is, as I told, the two different error metric we have considered. One of them is like, discrete version of mean square, I mean, absolute mean error, mean absolute error. Okay, this is basically L1 distance. So here, of course, my CIs are the actual output category. PIs are the category of the predicted output. So the difference. So that is the error. Okay, and capital T number of data points are there. Okay, so what we are finding out, and W is the width of the interval. Okay, so and rho is another. This is basically motivated from accuracy. So it is basically inaccuracy matrix. When it's more than 2, then we count how often it is more than 2. Okay, so if you think that this these small narrow strips are like bins, then this consecutive 5 bins together gives me a band. So this band, so yeah, so how often things are predictions are bad, like away from this band. So that is my rho. So 1 minus rho is the probability that it is inside the band. So these are the ways that we construct about our errors. Now we come to the point of how to do that, approach that, feature input variable, correct? I mean, so here's this approach 1, 2, 3 different things as I do. So the details about these three different things are here. So input here is the given stock price. We do not compute any moments or anything. We consider rather non-parametric statistics. So we take order statistics of the log return. Okay, and then we take 20 such data points. So then log returns give me 19 such points, and then we arrange it. And first one is called the feature 1, and smaller to higher, say, order statistics. That would give me 19 different parameters, and of course other things as I told, that contract parameters, that is the relation between stock price and strike price, that is moneyness, time to maturity, the difference between today's time and future time, that is time to maturity, and of course bank's interest rate. So that is about approach 1, and similarly approach 2 has little tweak here. So here we use more information of the intraday data, like open, high, low, close, etc. Approach 3, on the other hand, uses similar kind of things, but it includes also previous day option price. Okay, of course with proper scaling. So that is one extra information, and that actually we'll see later from the tables that makes this approach 3 much more perfect than other 2. And approach 1 and 2 are quite similar in performance. Okay, so these are some details about the architecture. So I'm not spending time here. Yeah, so that part I have just So then the result looks like this, that when we take the asset price, the option price data. So option price is very difficult to plot here. What we have done, rather, for every option price we calculated is corresponding volatility. So we plotted the implied volatility, and this red curve is the actual implied volatility, average implied volatility coming from the data. On the other hand, this gray zone is the band, what we are predicting from the model. So that is giving a visual that how these things are including. I mean, it is not that always it is at the middle. It is sometimes at the corner or sometimes outside. But what matters is that, these fluctuations are always, had to happen. And we are, so then it makes also difficult to judge whether this model prediction is, is doing well, or is it acceptable result. So what we do is that we try to compare with the suggestion of theoretical model, like, what we've taken Black-Scholes model. If I am I'm believing on Black-Scholes model, and from the data, I calibrate the parameter and then apply that and find out the option price from the Black-Scholes model, what I'm going to get. And I would then, check whether that option price and the algorithm predicted option price, they are, they are doing the similar kind of things on them. So that is the kind of, basically idea. So in the Black-Scholes option price, the error, what we have computed for this particular case, that NIFTY50 data, turned out to be 0.19. However, the average model, because we have trained the error, what the Black-Scholes error matrix also there is a list. Okay. So yeah, so this is one kind of checking that then this gives a confidence that okay, is capable of capturing certain things. Okay, so at least it is doing similar or a little better than the BS pricing. Okay. However, I also agree that BS pricing is is really primitive. Okay. I would not go into much more details now. I would just go to the next question, arbitrage, and yeah, and explore and understanding the algorithm. So here, what we see is that if we plot the predicted price on the horizontal axis and actual price on the vertical axis, we see this line, there is a red line, and green line is the is the orthogonal regression line, and then the closeness of that is a measure of the fairness of the price. Okay, so one can test hypothesis that okay, is it fair or not fair by comparing the coefficients of these lines. Yeah, so that is a data-driven way of in the settings. So this also, we have formulated, we have proposed that this could be a way to actually address arbitrage pricing in this scenario. Then we should talk about the failure that when this does not work. For example, of course, the COVID-19, then, whatever the algorithm learned was not in that, it learned a space which is far from the region where the asset price dynamics is moving on. So it failed to do much. So it is just QQ plot of depicting that earlier data and COVID and the Jan to March 2020 data and how they are not aligned. Basically, along this diagonal is like they are like similar aligned and not away from diagonal for people that they are behaving similarly. Okay, so here to understand better, we know this. And yeah, do I have 2 minutes maybe?
Yeah, yes, you can take 2 minutes. Yeah.
2 minutes. Yeah. So yeah, so this is basically the last slide. Yeah. So here we are trying to understand the reason that what is happening here. So what we have done is that we trained from Nifty 50 and test and bank Nifty, and there's a success, and then we combined. We trained both the a model with both the data and then checked. So here, this plot is actually exploring that thing that because these algorithms, how they, so what we have done is that we have simulated a family of artificial data, like the GBM data, and for artificial input output things, and test it, and then check that where
I think his connection just went.
Yeah, I think there's a disturbance in between.
Just
It will disturb.
5 minutes. Maybe he'll come back.
I think, I don't know, today also at my home, surprisingly, since morning it is not stable. Maybe a problem everywhere with the Airtel, I don't know.
Maybe some outage. I think there is an option to pause the recording. Should I pause it? I've never done it. Maybe I'll pause it.
that my
Yeah, please
connection
continue.
was,
Yeah.
But anyway, now time is over. I must stop. Yeah. So yeah, I would rather would be happy to accept some questions if there is any.
Okay. Thank you, Anindya, for a nice talk. Sorry for the disturbance. So, are there any questions from the audience? So, Anindya, I have one question. So, when you train the data, so how big the data is? Is there any kind of guidelines? Suppose, like, or did that depends on the model?
So generally, for machine learning algorithms, the data size should be large. Okay, so large means like 10,000 etc. kind of data. If one gets, then one can expect some some sort of accuracy. So, but for option pricing, we did not have scarcity of data because so many different contracts are being traded each and every day. So we had actually too much of data. So we removed lots of data because we focused on only near the money and a particular range of time to maturity. We had lots of data for every asset, whatever we. Of course, we have to look at those assets which is very popular and lots of investors are interested. But we had lots of data. So 10,000.
My question is not just having the data, but also
but
like
we had maybe
testing data also may involve some cost. Suppose if you have to do computations, that may involve some time, some kind of work, right? So that was my concern. So
I couldn't hear properly.
Having data is one thing, but other one is testing the data, like training with the data is also involves certain computations or some work. That's what.
Correct. You are right. Yes. Correct. So yeah, you are. I mean, very simple architecture for which training time would be reasonable, like within few minutes. And data size also we have reduced like 10,000 something so that it can run in any personal laptops in few minutes. So of course, if because our goal was not to find a very accurate result or anything, our goal was just to investigate the possibility of such approaches. But of course, in industry, if someone is really interested to use these things, can actually implement with better architecture and better and more number of data.
Okay, thank you. Are there any questions from audience?
There is one in the chat window by Goidik Chakravarti. I think, Goidik, you can just ask the question yourself, maybe.
Yeah, maybe I'm right.
Yeah, in the sense you can even read it because then it will be recorded.
No, actually, I'm using mobile. It is difficult.
I was
In this model, I saw that we are OI of a contract as a feature can or are. We also using the open interest of the nearby strike contracts or the same strike contract in different expiry for the forecast. No, I have not taken open interest as feature. Okay, there are some papers which has taken that open interest, but I have not taken open interest as a feature.
Okay, sir. Thank you.
Okay. Any more questions from audience? If not, let us thank the speaker again.
We have
Thank you,
actually
Anindya.
used open interest to, well, you are welcome, yeah.
Oh, okay. Sorry, there is a network problem. Definitely. The delay at my end.
I didn't catch you, sir.
Sorry.
Oh.
Even at the speakers end, I think there was some delay. Maybe
Yeah, completely messed up, I think.
it's unstable. He was saying it's unstable also today. Okay, let me stop the recording now. Now we can end the recording.
Yeah. So we are going to end the session officially.
Yes.
Apurva? Yeah, okay.
That's the end of this
Thank
session. The final talk of the symposium is in 13 minutes. And Mainak Poddar will in here.
In session 1.
No, in here. Right.
Here.
Yeah.
Okay.
We're already here.
Okay.
Mainak Poddar will join us and the final speaker is already here. So yeah, at 5 o'clock.
Okay.